We're happy to welcome all of you. Good afternoon, ladies and gentlemen. I am Ms. Malak Makram Maher, the student coordinator of the Math Club from the IT department at UTAS Muscat. It is my pleasure to welcome all of you here to this event. Today, we have before us a well-known speaker, Dr. Sharjeel Imtiaz, Principal Data Scientist Consultant, Hyundai Supply Chain Division, California, United States, to present on a case study of supply chain using linear programming and operations research. I am sure he will enthrall all of us once again by sharing his amazing knowledge on this topic. Now, I would like to invite our respected head of the section, Dr. Bushra Al-Sulaimi, to deliver some words about our department events.
Assalamu alaikum. Good morning, dear participants. This is Dr. Bushra, Head of Math Section, IT Department, University of Technology and Applied Science, Muscat. Today's talk is one of the series of events organized by Math Club of UTAS Muscat. It is indeed my pleasure to welcome you all to this presentation entitled A Case Study of Supply Chain Using Linear Programming and Operation Research by an expert speaker, Dr. Sharjeel Imtiaz, Data Scientist, Hyundai, California, USA. I am sure today's talk will be very informative and useful for academicians like us. Thank you.
Thank you, Dr. Bushra. Now it's time to learn. Let me introduce our resource speaker, Dr. Sharjeel Imtiaz. He is a principal data scientist, consultant, and researcher at Hyundai Supply Chain Division, Irvine, California, US. His areas of expertise are artificial intelligence and machine learning. He completed his professional doctorate from University of West London, UK. As a seasoned data scientist with over 16 years of experience in artificial intelligence and machine learning domain, experience mastering the development and deployment of complex AI models. His work experience spans in the areas of logistics, finance, healthcare, and sales. On behalf of the Math Club of the IT department at UTAS Muscat, I would like to invite Dr. Sharjeel to come forward and begin our session. Welcome, Dr. Sharjeel. You can start the session.
Thank you very much for introducing me. Let's start first a little intro with my video. You can see me, I think so, by face. A few of you already familiar with me as of my ex-colleagues, and it is a long journey to be in USA and to be in practical field in industry. So let's start with the case study, and let me introduce. Let me first brief about this topic. Uh, so it's very important to let all of us know why this topic is so important and so emerging. Reason is that that particular topic is right now emerging in the industry and very much in need. And I got basically I'm in supply chain domain in Hyundai, and I'm making a forecasting model there. And even we are discussing these case studies as well. And many of the beverage industries basically using linear programming. The beverage industry, especially using linear programming, and very interesting to let all of you know. Some of the beverage industries in New Jersey area, they're quite PhD in mathematics, and they must know the beverage industry, and especially for Omani students. Because I was part of this community, and I thought I should contribute. So this topic is especially good for them because if our teachers can prepare operational research and linear programming mathematically and programmically at the same time for the bachelor in the bachelor program, because there are a lot of need in the USA for this, and definitely that need will spread into Gulf as well. So let's start. So that's why operation research used in demand for supply chain, demand supply, and also it is used for resource optimization. So today's basically first we start with the introduction. What is linear programming? This is very important, and let me start. Linear programming, basically, we definitely in as a mathematician, some of my friends are there, they know better than me. And but as an introduction, and I feel that that students in Oman, they should, this topic should be in part of curriculum. That's my contribution to the society. So let's say, what is the operation research? We know that in the operation research in Python, basically, the operation research in the methodology in Python, we define the problem, and then we develop a model, basically, and that model solved by some library. That library you can see in the third box, its name is Pulp. That library solved this model, and we just develop a model and collect data. So first we define our variables, we develop our model, and solve this model by some library. So this is the idea, nothing else. So just to define your variable, develop model, and solve by library, just 3 steps. So like this you can teach the students as well. So I just adopting the same approach, so that can be simplified enough. So linear programming, we have the linear equations, linear expression, and information is actually has to pass for the students. So that's why it should be very base level. So the linear expressions, we know that it should be like in the form of equations. These we have the decision variables that must be real variables. Decision variables will decide, for example, the production related variables. These are decision variables. And we have the objective that must be linear expression. So we have objective functions as well. So can you see my screen as well, with my video? Okay. The objective function must be also linear expressions, and this is the linear expression equations. We know that we have the constraints there, and x1 plus constraint x2, like this we have the linear equations. No matter how many variables we have, it's like a linear form. So it's a very basic thing, like x1 multiplied by some value, constraint is there like a, plus b multiplied by x2. So like this equation is there. So if you put a condition there, that become constraint. So very simple, a x1 plus b x2 greater than some value, less than some value, so it become constraint. This is the concept. So that constraints must be also the linear equations. uh, 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 so, uh, so, uh, these constraints must be linear expressions. Linear expressions are any expression of the form. So linear expression can be any of the form. So let me give you the um, of what are different basically variables. We have decision variables like x1 x2 variables. So these are basically so I'm jumping over, so let's elaborate a little bit. These are basically decision variables. So we have these variables, and we write these variables in the form of linear expressions, and to basically uh, so basically these are the variables and decision variables, and this is the basically problem is this is a very simple problem. First we see the problem, and then I define the Python function. Sorry, I'm jumping over. We have a cat food, for example, and there are two ingredients, x1 and x2, right? So we need to see that the chicken and the beef, there are two variables. So the percentage of the variables in the food container. So we need to find out how much percentage we need for these variables. So this is the problem. So identify the decision variables. So we need to find out x1 and x2. It means percentage of the chicken used in cat food containers, percentage of beef used in cat food containers. So this is our problem. So how we define our constraints based on this problem? Uh, uh, we have the constraints on the variables, are they must sum up to 100. So we have these constraints. I told you all of the conditions and constraints must be in the linear form. So I will explain this programmatically as well, then it makes you more clear. So what is this theoretically? We just see the conditions. So based on these condition, we put some of the condition that sum up to 100. Some of the conditions there, and with x1, some of the conditions uh, like some of the values which multiply with some of the other variable, that is for the beef. X1 is for the cat. How much percentage we need for these nutritions, we multiply some with some of the constant value, and that value is basically we just compare with some of the that is must be greater than zero point 0.8. So the answer should come greater than zero point 0.8. So we say this constraint meet is true. Similarly, we define these five constraints in this way, and uh, we now see we will see the programmatically how we define these five constraints, and how the linear programming solved, and what is the problem we need to find out. Basically, we need to find out x1 and x2, and we need to find out what percentage of chicken we need and what percentage of beef we need. So that percentage is basically need to meet, and that should be minimum cost should come for that particular ingredients percentage. So that is our objective functions. So let me share another screen. I hope mathematical background people have more understanding than me. But we just see how the linear programming solved empirically. Now, this is the language. So we are talking about the linear programming. So the language give you a research methodology which I explain you. We create the variables, we build the model, right? And we solve the problem. So that's it, these three steps. So first of all, we create the variables. There is a library here. The library, you can ask some of the IT guys, where that is easy to install. The library name is Pulp, and you can, if you have some background of very simple Python language, you can install this library by this command, or you can ask some of the IT people, so they can help you. Just use this command; it will install automatically this library. Now the other question, the description is there. This file I will share with you guys later on. It is describing what is this step, and even there is a in the slide the link is available, which you can navigate to see the details of these things. So overall, these libraries explanation also in the slide. So I'm not jumping over that particular slide. Just defining what is linear programming, introduction and problem example. So then we go to the case study. So here we define the variables. Variable defined by, first we define the problem. So we create the problem, and the problem is basically viscous problems to minimize to find out x1 and x2. So we have to find out percentage of basically chicken and the beef. That's it. In the container, in particular container for the cat food. So here, as I told you, this beverage industry and food industry is using this example as well. And there are many other industries which are using these example. So here we define just to the function objective. Objective is to minimize it. So what is minimize? There are two types of objectives: either to linear programming minimize the cost, or either it will maximize the production. So we are minimizing here. LP minimize mean we're minimizing the cost. So defining a problem is defined by this variable. This variable you just use in the bracket, you write your problem description, and objective of the problem is to minimize. So you define the problem like this, and your problem is defined here. Next, you create the variables. As I told you, first define the problem, then you create the variables. So here the variable is x1 is chicken percentage, variable x2 is beef percentage, and it is data type or any quantity you want to give. Initially it is 0, so we don't know what are the percentages. So two variables we created with lower limit of 0 means we don't know basic, like x1 is equal to 0 or x2 is equal to 0. So like that, those equations. So we just define two variables. So these two variables now began collecting problem. So here is we define the third step is to define the objective function. This is important step. So you have linear equation. As I told you, we have the linear equation, and we define all our decision variable linearly, and we define all our constraints linearly, right? This is our basically linear decision variables, and which we define linearly as a objective function. So objective function, what it do, it takes the input, its objective is to minimize the cost and maximize the production. So this is the objective function in operational research. So we have x1. X1 is our chicken percentage, x2 is our beef percentage, and we always use problem. So problem we define here in the first line. So here we just add it with this objective function, and we use this operator plus equal, and we add this objective function with comma. So and write down after the comma the description of the objective function, the total cost of ingredient. Basically, we are want to find out the total cost. And that would be minimum. So that is what we have done in this step. So we define so whatever the value of x1 we get or x2 we get by decision, basically these are decision variables by linear programming implementation, objective functions and constraints. So that the output will come basically minimum cost and percentage of ingredients for x1 and x2. So next step, we define the constraints. So here you just in the slide you see some of the constraints. So what are those constraints? Those are also I told you, like objective function, linear equations, but with some of the conditions. Like we have the first objective 5. There are 5 constraints. Like if you add 2 ingredient, it become 100. That is percentage, basically total usage, total ingredients. And another constraint is telling if you have some chicken percentage multiplied by some 0.1 per 100 and 0.2 you multiply by beef x2 percentage, that should be greater than or equal to 8. So it should be greater, the value should be greater. That is protein requirement. It's telling this is protein requirement. So the fat requirement must be greater than 6%, and the fiber requirement must be less than 2%, and salt requirement, the third constraint, is must be less than 40%. So these are all constraints and these are our ingredient requirements. So now we define these constraints. Now all the problem data is entered, and we define our variables here. Just initialize here the variable first line, problem initialize, the variable initialize, like you define the mathematically you initialize variable with 0, or you define the problem like first line and then define the variables. Then you define the constraints, objective functions, your model, and then your constraints, these constraints, 5 constraints. And then you define, you write down the data into problem. So problem data must be written into the one file. That file name is, we have to give in programmingly, we write all our data to one file, and it is solved inside that file, and that is hidden from us. So there is a function to solve this, that is the function name is write LP, linear programming, and inside this file we write everything. So using same variable problem, we write everything inside this file. When we call this function, your constraints here, this last step, and your objective functions all must be written automatically inside this file. So now when you run this step, also you see there are 2 functions. It is telling the beef percentage and the chicken percentage. That is your problem, and that problem you define with these 2 variables. So your problem is defined and description is written there. You can read this description, and easily you can understand the LP problem. Further, we solve using pulp chooses. So pulp, what it do, it solve is automatically this problem. When we call this function, it solve the problem. So when it solve the problem, what it give? It give you the optimal. It will give you the optimal percentage of value for the chicken and the beef. So we want, now it's solved, and we want to see what is the optimal. There are 4 decisions it makes: not solved, infeasible, unbounded, undefined, and optimal. So it can be possible with your constraints. It cannot be solved. Your constraints are incorrect. So it would be possible your constraints are correct. So when you click this, it's telling your optimal, means your problem is optimal. You're getting solvable problem. If it is your constraints here are in mistakes, or your variables objective functions is not correct, then it will say it is not solvable. Or some of the problems like that in linear equations not solvable as well. So those problem it will categorize as not solvable, and it is a tool for mathematical teachers to solve some of the equations, and it is a tool for bachelor students to solve some of the linear equations like this. And it is very basic thing, and you just call these functions to solve it. If it is solvable, you click here, it is telling optimal, means solvable. If it is not solvable, it will say not solvable. And it is also for research. If you define some of the questions in your master's students in Oman in master's thesis, and students in PhDs, they want to check their hypothesis, or they want to see their operational research with whatever the decision variables or production variables they are finding out, they are correct or not, or their constraints are okay or not. This is the tool to like a diagnosis for them. And then the variable, if it is solved, it will get print. We want to see what are the optimal values. We find out based on our constraints, and we find out that 66% of the beef and 34% of the chicken amount we need for x1. X1 is chicken percentage, x2 is for beef percentage. So this decision variables will help us to solve our objective function. So optimize objective function. So what is objective function? We need to find out minimum. This is our objective function. We have to find out total cost for the container. This is our objective function. So we substitute these values like 64 and 66 and 34 here, and we get the cost. So it will give you the cost here, and it is giving 97 cents. So this is the final outcome of this optimized objective function. So this is the minimum basically cost uh, based on your problem. And let me go back to the slide again. So far, this type of basics we needed, and we have some of the link here. If you want to see this problem is also there, and I just run this problem in the Python, and you can see the description of the problem in this link. After we will share the organizers will email all of the participants, and you can just even include from here. You can see the library descriptions, and if you need my help further, I can guide you. Uh, Here we have minimize this function, so already it is a fixed value there, and x1 x2 we have to find out. So this we have done, and the programmatically it is written here, the description, everything what it do. I explain you the same thing, and then we find out basically uh, the uh, finally we find out basically the same steps I followed here, and this description I just explain you in my words, and we find out the percentage of the value and total cost. So it is concluded here. We have 33%, and the total cost of ingredient can be 96 cents. So total cost must be minimum. So we find out that cost. Similarly, there is a more description here. If you want to get into more details in step by step how it's solved, you can do and extend this problem in your curriculum, and for the students with the full solution is available here. And not only this, there are many problems. These are very simple problems. When you have a good hands on these problems, the food problem, and literally I'm telling you, you can solve the industry problems as well. This is the basics for those problems. I just have to guide you what is the right direction. So this way we can get into this, and we already professional, so we should, and many students here get help from the teachers as well. So I think so I'm just guiding only. So next, let me share the slide. Hope you can see the slide. This link is there. You can follow the documentation link. An example is there, and linear equations are there, and very simple steps. Initialize the problem, initialize the variables, and next step you have to basically write down your objective function, and you write down your constraints, solve the problem, get your optimal value for the cost. So these are 4 5 very basic steps, and this way our linear programming work and operational research work. And next, we have basically a case study of supply chain. Supply chain domain basically uh, basic supply chain domain nowadays in the we this case study is about the plants, and plants are coming from many. There is a more demand in USA for the plants. So plants are coming from many of the big countries and small countries as well. What is the problem? Problem is this to uh, demand forecasting. So how much? How from where we get the production? From India, from Brazil. So main thing is production. So how much production we need and from where we get it. So here the decision variable is basically the how much production we need. And total cost must be minimum. Same thing. We have to minimize our cost, and the total production and which factory. Decision variable will tell us we get from the high factories in from India, or high factories from Brazil, or high factory from China. So there are different factories. Are there high plants and low production plants? So which type of plants will get our need to fulfill, and where we get it? So location. So this is the objective, basically objective function. So variables are here basically to find out the um, location and the plants locations. So here we have the fixed production cost. We have basically different variables here. We have fixed production cost of your facilities, dollars per month, and variable production cost per unit, and shipping cost and customer demands. So these are different basically variables, like you see X1, X2 like this. So we have different categories of variables here. So here the problem, should we keep outsource? Uh, the problem is that we should be keep outsource with shipping costs that have tripled the last 12 months. So what is that problem? So I told you that we have some of the basically factories in India, and some of the factories in Brazil, and some of the factories in China, and we need to know for which high demand plants we need from which country. That's it. So this is the question. So who will fill up the demand in USA based on the because the shipping cost is tripled, and the last 12 months, how we fill up? So we have to minimize our cost. So basically the same objective function, minimize the cost, and decision variables will tell us the some of the amounts, percentages. So that will tell us the some of the numbers, and we minimize our cost there. So this is the same thing we have to do. And next, we have the problem statement. Basically, you want to refine the supply chain for next 5 years. You must consider increase in shipping cost and forecast of customer demands. So basically, shipping cost is increasing, and so you want to supply chain network is there for next 5 years. So forecasting the customer demand. So for next 5 years, you are forecasting. So there are different regions here, different countries, as I told you, different oceans, the different lands here, India, and we have different 5 lands here, and you will see their names here: 5 markets: Brazil, USA, India, Japan, and Germany. So here are two types of manufacturing facilities: low capacity and high capacity. And for example, in India, we have the low capacity plants and the high capacity plants. Similarly, in Brazil, we have the low capacity and high capacity. Similarly, in USA as well. So each location, each market is having low capacity and high capacity sites. Then we have the shipping cost. So the everything, for example, I'm in car industry. So I'm working for the supply chain domain, and for costing model I'm building. So it is very challenging problem. It's not academic problem. It's very industrial problem, and it's very challenging. I have to forecast for next 30 days for that the car will be delivered when it land at the port. It's not one car. You can imagine one day 6,000 allocations, 6,000 cars arrived at the ports, and 48 states. So in USA, so it's very challenging, and it's very like a PhD research. So because there is a lot of noise and very challenging data. So similarly here in industry, an academic is a basic. Basic should be clear, and if your academics is good, your basics is good, very simple in the simple words, then you can do the advanced things easily. So that's the main thing. So students should adopt the similar way. That's why I'm sharing my thoughts. So shipping cost per container is there, and then customer demand per unit per year is there. So next problem statement is that uh, so just I'm skipping this problem statement. It is in detail. So let's see the cost depend on the country and type of plant. So here we have cost per month for USA like 6,500 and 9,500, basically high plants. Germany, low plants 4980 and high plants 7270. Similarly, in Japan 62309100, and in the end we can see the low cost plants in India, and their cost is 2110 and 3080. So remember, the main objective is to minimize the cost and maximize the production. So this is the main objective. So production variable costs, production line operators and raw material. So here we have per unit, basically raw material per unit is there, like 1 unit. You can expect like Germany is giving production raw unit is 12. Germany is giving, for example, 13 $13 per unit. This is the price of the cost of the basically raw unit, like 1 unit. So here this is basically in dollars, the low cost and high cost, and this is in per unit cost. So next we have basically uh, uh, we have the problem statement. For problem statement, we the variable cost a unit produced in Germany is $13 per unit is written there, and one container can contain 1,000 units. One container can contain 1,000 units. So if you want Germany to Japan, it will cost you. You can see this table, and you can make decision for if you want from Germany to Japan, it will cost per container 1231. So here you can see in the table 1231 is written there to Japan. So the column or column you can see Japan, and the row is Germany. So Germany is mapping with the Japan 1231. So this is the cost per container for if you want to send to the Japan. So this is the shipment cost. So we have the shipment cost and we have the per unit cost. So if one container is we are taking, so definitely the per unit will multiply with the 1,000 units in one container multiplied by unit and equal to total basically the cost for taking to the basically through the container. So next, now we have the manufacturing capacity by side, a high capacity factory. I make it very shortly and important information. It's not useful to drag in detail because something audience just have to get idea and explain solve by themselves as well. Can produce now high capacity per month. Brazil high capacity factories, they have the Brazil having the high capacity, and they can produce 150k units per month. So next we have, let's try customer demand per market scenario. There are three scenarios. Initialize the parameters. Scenario 2, we increase the production in the India. Then surging cost due to container shortage. So basically there are three scenarios. So here USA demand is this much, Germany demand is this much, Japan demand is this much, and India demand itself for each country is this much. So there are three scenarios. So now we substitute those variables. High capacity plants, Brazil, for example, cost is coming per month this much, and Brazil to USA cost is coming this much. And then high capacity and one low capacity we will see. India plants produce for all countries except Germany, Brazil. This is the constraint. So they don't basically produce for Brazil. So there is a India to Germany 90,000, India to India the the total units per month that much. Per month how much? So India to Japan 200K and India to USA that much. So then we need to see Japan need to produce locally because limited capacity of India. India is having low capacity, so that's why Japan is producing locally its production in the plants 150 and so total cost for the is coming six to this number 62038 triple zero. This per month total cost is coming. So now we will see scenario two. Scenario two is telling if we double the size of high capacity plants in India, let's try to double the size of high capacity plants in India. And Brazil is still producing for local market and the USA. So here we have the plants, high capacity plants. We double their capacity. So after doubling the capacity, the total Japan does not produce locally anymore. So total capacity, total amount, this much is coming. And next we have the third scenario where we surging shipping costs due to container shortage. We take basically more plants from the India, and shipping cost we increase. So more shipping cost we incur. So that's not a problem for USA. So they want to take more plants from there. And that scenario three, we substitute some of the units per month at their capacities. So next total cost after shipping cost surging, total cost is coming this much, and that is the final cost. So now we try this thing. I know this is very complicated to understand this way, but I hope we get idea. Just that's enough. So here we have plant locations, we have different variables. Now we will get more understanding. So here we have uh, we have a manufacturing variable cost. These are manufacturing. This file is having. I will share this file, and this file is having all the units variable yani per unit cost per plant, one plant cost. Okay, for USA for 12, Germany 13, like that. So India 5. So freight cost. Freight mean their when they're shipping the import cost, how much comes. So when I read this file, so it's selling USA to Germany $12,250 cost coming. So for India is coming 13,650 cost is coming. So like that, if India to USA, we send the container. So this is the shipping cost. Then the variable costs. So here the free cost divide by 1,000 maneuver cost, and these are the different variable costs along with the container cost, freight cost per container cost. We are calculating additional cost. So these additional costs we have to add, and for example, Germany to we and it's coming in basically in small amounts like 13 and 10 and 36. So these we add together with the freight cost. And then we have fixed costs, the import cost. The import cost, for example, Germany to Germany is having 4980 for low plants and 7270 for high plants. India is having 2100 and 110 6160. So now the plant capacity. So plant capacity 500 capacities, and for all the plants is having 1500, and India is having more capacity, 3000. So now we demand we define variable like okay. Now this one is we have to skip. Now we here I'm defining the same variables here using LP variables, and all those variable which I define here, all those variable using programming, I'm adding as a dictionary in this LP variable as a dictionary. So then I define X and Y, the CN variables. So these two variables are defined and then define the objective function. So similarly, first define the problem. Problem is this one, and model define, create the variables this line, and this line we define the objective functions. Here we define the constraints. So all those constraints are written here. So in the form of a loop, we just add up into the model, and we define some of the constraints in the slides as well, like so those these if high capacity plant in USA uh, is open, then the low capacity plant in Germany is also open. So this is the constraint. So these types of constraints are there. So if high capacity of USA branch is open, then low capacity also open. So in the loop, we just add up into the model in linear equations. And just we solve this problem. When I run this, it's running. So that what happened, I get basically total cost here, and that will be my optimal cost. And in the end, I'm just printing which site. Actually, I have to find out which site is more
Excuse me,
suitable.
Dr. Sajid. Can
Yeah.
you just change the slide, please?
Can you see the which one?
Because it is just empty. Do the case study in Python, it's showing. Can you please change it?
Now you can see.
Yeah, fine. Thank you.
Okay. So in the final step, uh, you didn't see the program before I was explaining?
No, past 2 minutes, it was in that slide.
Okay. Let's explain here again. We define our decision variables using location and size. And we initialize our model here like a problem. And then we define our decision variables using dictionary. LP, the variable is basically we use as earlier I explained. And here we define all our variables from production and the plant. And before you see the plant variables in SCAP in this frame, and the production variables here in manufacture frame. So like this, basically, we will do that. So here we define all our variables and add them linearly using and we add them LP sum, so it will do the sum operation. And add these objective functions to the model, and after that, and the variables, fixed cost and the variable cost. So both fixed cost and variable cost, which I explained earlier, it will be added to the model, and constraints will be added there. Using these are linear equations basically. In the loop, I'm just writing. You can say one linear equation, then add them other linear equation in the loop in the model. So we adding them in the loop to the model. So here it is in the loop to the model is adding, and loop is like for loop here you can see. So when you go into detail, you can understand that. So just giving you idea. So we write the same step to model to solve this problem. What is the problem? We give all the variables cost and the plant production capacities, and we just solve. We want to find out the total minimum cost. So we just total cost. The objective of function is total cost. So the output is coming total cost is this much. And we next step we want to see how much what are the different locations where we get this total cost. So USA, one high plant, and one Japan, and one India. So that's it. That is it. Any my actually last slide should go, and I will finish talk, and I would have some of the questions. Basically, the model gives you flexibility to we don't have to go into programming details right now. You can learn these things, linear equations, how we add into variables and objective functions, and then we add them together. How we do that, step by step, we can understand it easily. and we have some of the function named solver. It solve the problem, and just printing the optimal values. Just print the optimal values. There is a function. So all things are available. You just have to use it. So scenario is telling basically scenario 3 that works for us. That cost will be minimum when we surge the shipping cost. So definitely we get the minimum cost. So this here I will end this use case, and there are many other constraints we can add together with this use case if you like to. And this reference for the documentation for this library with simple examples you can find from this link. And this is use case is used in industry, so it is hard to explain in few minutes even, but I just give you steps. So those steps similarly followed in professional industry. So just in the loop. So you can see that these are linear equations defining constraints and define your different find out your decision variables, and find out your minimum cost. So this is the main objective function. So any question I would like to ask, if you like to ask for me.
Thank you, Dr. Sharjeel, for your excellent presentation. Now comes the question answer session. Dear audience, you can ask questions now, or you can type your queries in the chat box.
Yeah, please.
Hello,
Yeah, I can hear you.
Professor. Good morning. Yeah, good morning, Professor.
Yeah, good morning. In fact, here, good night.
Nice. Oh, good night, Professor.
Yeah.
Thank you, Professor. It was a great presentation. Could learn something from your talk, right? Professor, actually, myself and my scholar, we have worked on the supply chain management and along with optimization technique. And the only thing is sometimes in journal or in any presentation, they ask, what is the complexity of your algorithm in getting the optimal value?
Right now, the complexity, the complexity in this algorithm, in terms of which, you mean to say the cost, or you mean to say the decision variables which we are finding here?
Variables only, Professor, not the cost, Professor, because we are trying to let down the trade-off or the balance between the cost and this optimal solution. But the problem is with variables.
See, yeah. So you are questioning the same thing which I answered in the last slide. We have 5 different decisions available when we define our constraints and decision variables. One is not solved, one is infeasible, one is unbounded, one is undefined, and one is optimal. So you can see when your decision when you're in, for example, your constraints, you can see the slides here. When your constraints are not well defined, you will get some of the status like infeasible. So this is your complexity. Actually, it is infeasible, or some of the answer come undefined. Maybe one of the your constraint is not defined well. Or maybe some of the value is very highly defined. So then the complexity is not unbounded. So unbounded, very high. So this, like this, when you use this library in simple steps, you will see these 5 status. When you get optimal, it means you solve the problem. So otherwise, you get some of the unbounded and complexity. So you have to substitute your problem into this library, and you have to find out your type of complexity. So that's according to this library, this is the answer. So I'm giving the solution here, the tool which will help you to find out the particular type of complexity first, then you can reduce that.
Okay, thank you, Professor. Thank you. This is Vijay Lakshmi from Central University of Tamil Nadu. Thank you, sir. Thank you so much.
Welcome, welcome.
Okay, once again, thank you, Dr. Sharjeel, for the wonderful session that you presented here. It was really informative. I'm sure the audience would have gained a lot of your inspirational presentation. We are expecting some more sessions from you in the future too. Thank you, Dr. Madhusudan, for introducing such a knowledgeable resource person to us. Best of luck and have a great day.
Thank you very much. Thank you very much for inviting me. And next time, anytime you like to my service, particularly for the sessions, I'm available. Thank you very much.
On behalf of our head of the section, Dr. Bushra Al-Sulaimi, we take immense pleasure to award the certificate of appreciation to our resource person, Dr. Sharjeel Imtiaz. Well, ladies and gentlemen, that wraps up our session. The participation certificate will be generated automatically once you finish the event feedback. The link will be sent to your registered email address. On behalf of the Math Club of the IT department at UTAS Muscat, thank you all for making time in your busy schedule to join us here. It's been our pleasure to host this event, and I wish you all a pleasant day.
Thank you, ma'am.
Thank you.